The next one, which is strongly connected to PCA, is MDS, multidimensional scaling. So multidimensional scaling is quite a simple idea. When we have distances between all the pairs, then we know how to make a map. Okay, so think about this one. So we have 3 points, and you know the distance between the 3 points. Then you can draw a triangle, right? Yeah, there is an ambiguity, like this triangle can rotate and flip and transit, okay? But still, we can find the shape of the triangle. Likewise, we have another example here. We have a distance matrix between the 9 American cities, okay? Boston, Chicago, DC, Denver, etc. Okay, so as long as we have the distances between the cities, then we can find a map. Okay, this is how we make a map before GPS, long time ago. Okay, so we actually measure the distance between the mountains and between the rivers and the mountains and between everything. And then we draw a map based on this distance. Okay, so MDS will do the same thing. Actually, MDS includes a lot of variations, but we're going to focus on simple basic algorithm. Okay. So let's say we have a distance matrix D. Okay. And then let's assume that a data matrix X is like this. And obviously X is not given. Okay, but let's assume that since we have n by n matrix for distance matrix, so we know how many samples are there or how many cities are there. So let's assume that we have n points, okay, even though these points are not given, okay, so it's kind of imaginary point. And as I said, we're gonna talk about some basic classical scaling method. So in this method, the distance is Euclidean distance. Okay, so distance is Euclidean distance. Then even though we don't know, we don't have these points, but we know this distance can be calculated in this way. Okay, good. And this square can be represented by these equations. This equation is coming from this one, simply. And C is the vector with diagonal elements, and the 1n is just an n-dimensional vector whose elements are just ones. Okay, it's a simple vector. Okay, so we have d square, and we have inner product here. So this is important thing. So we have a distance matrix and the inner product matrix. Okay, so we're going to talk about this one later. And let H be like this. And this is a centering matrix. Now we're going to use this equation one more time. We put H left side and right side like this with another constant minus 1/2. Okay, then when we drive and rearrange the equation, then this one will be x transpose x. Okay, so here's the deal. Given distance matrix, then we can calculate this one. Okay, then we assume that this distance is a Euclidean distance between the data points. And then this one is actually x transpose x. Okay, then we can apply eigendecomposition to this matrix like this. Then look at here. This is x transpose x, and then we can decompose this equation into Vm lambda m 1/2 and lambda m 1/2 over 2 and Vm transpose. Okay, so this one is X transpose and this one is X. Do you see that? This one is X transpose X and we have eigendecomposition. So now X is like this. This might be a little confusing. X is not given, okay? X is not given. Only the distance matrix is given. And if we assume that this distance is a Euclidean distance of the data points X, okay, then when we derive the equations, then the d square can be rewritten. And if we multiply H, then this one is X transpose X. So given a distance matrix D, then we can calculate this one, okay? And then we assume that this one is X transpose X. So we take eigendecomposition of this matrix, then we will get the V and lambda m. Then lambda m to the power of 1 over 2 times Vm transpose is X. Okay, this is the simplest MDS algorithm. Okay, and then there are lots of variations, but we're not going to cover all the other variations here. Okay, this slide is a little off the topic, but I want to point out that sometimes the distance matrix is not a distance matrix mathematically. Okay, so in real world, many relations are asymmetric, like the distance in Google Map. You know, when we actually check the distance from Pohang to Seoul and from Seoul to Pohang, actually technically the distance is different. Okay, sometimes there's one-way street, sometimes we have to take a U-turn. So technically, mathematically, it's not a distance. Okay, and then think about the world trade data, and this is not a distance. Okay, so importing and exporting are not symmetric. Okay, so in this case, distance matrix is not a distance. Okay, and the column matrix from asymmetric relations is not positive semi-definite. So if the inner product matrix is not positive semi-definite, definite, then the distance which is implied by the column matrix or inner product matrix is not a distance. So it's basically the same thing. You know, the distance should be mathematically a metric. You know, to be a mathematical distance, then there are 3 conditions. Okay, and if the distance is actually mathematical distance, then the inner product, which is derived by this distance, should be positive semi-definite. Okay, but if the kernel matrix or inner product matrix is not positive semi-definite, then distance is not a distance. Okay, but in reality, in real world, we have this kind of cases a lot, as I said. And again, if the kernel matrix is not positive semi-definite, the distance is not a distance, and it means it is broken actually, mathematically in theory. But there are some papers saying that even the negative eigenvectors have their own meaning. Okay, and that is enough to say for now. Okay. Now we have a PCA and MDS. We understand how they are working from the principles. Okay, so let's compare PCA and MDS. That's quite important for the next topics. Okay, so for PCA we use a covariance matrix, and then the projection is based on the eigenvector. Okay, and then if we multiply this eigenvector to original data, then we can have projected vectors. Okay, and this one is eigendecomposition. And in the MDS, we have gram matrix or inner product matrix. We assume this one. Okay, so basically we have distance matrix is given. So from this distance matrix, by multiplying H, then we get this matrix. And we assume that this is actually X transpose X. Okay, and then if we take eigendecomposition of this matrix, okay, or B matrix, then projection is based on this. Okay, look at this one. We don't have X here. We don't have X here. We have eigenvalue and eigenvector. Okay, that's the projected vector ym. Okay, then I want to see the connection between these two projections. Okay, from here, b times vm is lambda m vm, and we multiply the same thing here. Then look at this one. This one is a diagonal matrix, so we can change the order. Then we get this one. And if we look at this one, okay, x, and b is actually x transpose x. Okay, then this one is actually covariance matrix. So we can rewrite this term with this C and X and VM. And then now, this one is exactly the same as this one. So this one is supposed to be the same as this one. And look at this one. We have a C and we have X VM here. X VM is a vector. Okay. Then this one is eigenvector of C, and this one is eigenvalue with 1 over m. This one is eigenvalue of covariance matrix, and xvm is eigenvector of covariance matrix. And the covariance matrix, the eigenvectors of covariance matrix is actually VP. So we have VP and xvm is eigenvector too. So VP is actually proportional to xvm. Okay, so we have connection here, VP and VM. Okay, and alpha is to make this one to be a unitary matrix. So if we if we use this equation, then we can make a transition from YP to YM. Okay, so look at this one. So YP is coming from here, and then we use these equations, etc. So you can actually figure out how to make these derivations. Okay, it's not that complicated. Okay, so from the previous slide we learned there is a connection between inner product and distance matrix and PCA and MDS. Okay, so we want to drive a PCA in a different form, which is really important for the kernel PCA later. Okay, so PCA finds W to maximize this Rayleigh quotient, and this is really tricky part. W is eigenvector, but we can rewrite W as x times alpha. Let's assume that we have lots of samples like this. And if we have eigenvector, okay, then this eigenvector can be represented by these data samples. Okay, let's say this is our eigenvector. Then this eigenvector is in this two-dimensional space. Then based on these samples, basically these samples are kind of spanning this space. And because these data samples are spanning the space, then any vector can be represented by a weighted sum of these data samples. Right. What if we have data samples like this? So in this two-dimensional space, data samples are actually in the one-dimensional space. It is embedded in the manifold is one-dimensional, which is embedded in two-dimensional space. Okay, so what about this case? So the X cannot span the two-dimensional space, but it doesn't matter because if we have eigenvector, then the eigenvector should be in this vector. Okay, it cannot take off. We cannot have this kind of eigenvector at all. It should be in this manifold. Okay, so no matter what kind of manifold we have, the data samples generate, this eigenvector should be able to be represented by a weighted sum of data samples. Okay, so we can rewrite W with x times alpha. Okay, alpha is weight and x is the data sample set. And then we can rewrite these objective functions. Okay, so this one was like this, and then instead of W we can use x alpha. So W transpose is alpha transpose x transpose and C x alpha. Okay, and now we can replace this covariance matrix with x transpose. Yes, there is 1 over n, but this is not important, so we just cancel. It's just constant, so we are not interested. And if we look at this equation in a different way, then we have two inner product here and one inner product here. So instead of C, now we have two B's and one B. So this one is our new objective function, and this one is eigenvector. Eigenvector is the largest eigenvector is the value of this one, and this one's eigenvector and eigenvalue is exactly the same as this one. Can you remember the Rayleigh quotient? And if B is invertible, then we can simply contrive this one. And we are not interested in eigenvalue 0, so simply we can use this objective function. Okay, then we have a little different primary alpha. Okay, so instead of W, we need to know the alpha. So if we know alpha, then we can define W. Okay, so we just change the parameter from W to alpha. Okay, alpha is the first eigenvector of this inner product or gram matrix. Okay, so we'll talk about this gram matrix later in column machine slides. Okay, now the projection of X is this. If we have eigenvector of covariance matrix, then it will be W. So Y will be W transpose X. This is conventional PCA. Okay, then W is actually X times alpha. So we have a different equation, and from this objective function we can find alpha. Okay, and then X transpose X is inner product matrix, so this is our solution. So instead of using this conventional PCA, we can use this one as our solution. So it's quite similar to the relationship between PCA and MDS, because MDS was based on the inner product matrix and PCA is based on the covariance matrix. Then there's a connection between the covariance and inner product, and based on this connection, then we have different kind of solutions for PCA. Okay, so this one and this one is exact same, right? But from different source of information. And why do we have this equation instead of this one? Think about this. The matrix, the data matrix looks like this. Features. And this one is sample and this one is features. Okay, so the number of samples is larger than the number of features. Then the covariance matrix is looks like this, feature by feature. Okay, then the eigendecomposition is not that complicated. It's okay, good. But what if the data sample looks like this, sample and features? Then the covariance matrix look like this. Okay, and if the number of the feature is hues, then this matrix will be hues, and eigendecomposition might be a problem. But in this case, if we have an inner product matrix, the size of the inner product matrix will be f by f. Okay, so depending on the number of features and the samples, then we can use a covariance matrix or we can use the inner product matrix, and we can have the solution, the same solutions. Okay, for example, if you're working on the genetic somethings, and in that case we don't have that many samples, but the number of features are huge. So in that case, so we cannot work on the covariance matrix because the size of covariance matrix is huge. So it's kind of detour. Okay, so we can solve that. We can get the PCA solution based on the inner product. But many times, usually the number of samples is way much larger than features. So usually the covariance matrix is better than the inner product matrix, but sometimes it happens. Okay, and this is all about the training samples. Okay, then what about the new point x sub t? Then y sub t is W transpose x sub t in the conventional PCA, because in the conventional PCA we have this projection map, okay, from the training samples. So now as long as we have a W, then we know how to project. So if we have a new samples x sub t, then it's just simple, just to multiply this sample, just to calculate the dot product between the W and x sub t. That's it. But if we have a PCA solution based on this inner product, then it's a little more complicated because W is x alpha. Okay, it looks like this, and then xt, which means if we don't have W based on the covariance matrix, then we have this. Okay, and then we have to multiply x sub t to this vector and matrix. Now on this slide, I'm going to talk about how can we use PCA in other applications. Okay, so you don't know what a regression is yet, but don't worry. Let's say a regression is kind of algorithm to estimate something or to predict some things. Okay, and when we have a lot of features, then based on some algorithm, then we can estimate the output y. But instead of regressing y on x directly, then we can apply a PCA to x. Let's assume that the x is in a high dimensional space. And in that case, as I said, sometimes we have some overfitting problem or the curse of dimensionality. So instead of applying this regression directly on x, then we just reduce the dimensionality based on the PCA, like this. So we have a low dimensional features, and then we apply the regression here, and we have the solution. Because this regression would be simpler than before, because this one has lots of features and this one is small features. Okay, this one is more stable and better. So PCR regularizes the model by using a subset of components. Okay, and then, however, when predicting the outcome, the PCs with low variances may also be important. So this is kind of limit of a PCA. The PCA is interested in the variance. When we project the samples onto a low demand space, then we want to keep the variance. But sometimes the variance is not important. Important information is hidden sometimes. Then we have to extract those informations. Okay, but PCA doesn't know which kind of information is important. It's just interested in the variance. It's just interested in reconstruction error. So in the classification problem, PCA might be not the best choice. But sometimes there is no other options. Okay, then the PCA would be kind of practically the best option, but it is not always the best option.